Hello everyone, my name is Samuel Derek Joga, and I'll be taking you through the agriculture stock prediction system, which is a machine learning based solution designed to forecast agricultural commodity prices, optimize inventory management, and provide actionable insight across agricultural supply chain in Uganda. Um, to begin with, our the, the overview, the project objectives are mainly to predict agricultural product prices, optimize inventory levels, provide interactive visualizations as in the paper, and then reduce price volatility, minimize waste, and improve farmer decision making. The key features in this system, there is price prediction, which is done by regression and ensemble models, time series forecasting, that is by the ARIMA, Profit and LSTM models, then inventory optimization, which is implemented using deep chew learning and true learning, which are reinforcement learning models. Then I'll have this interactive dashboard, which is web-based visualization and model comparison with the performance evaluation. So the project faces data collection, exploratory analysis, feature engineering, model development, system integration, and then deployment and monitoring. So as you can see, these are the green. The green is our progress, and all of them are finished, and we're currently not yet done with the deployment and monitoring, but others are done. So this is our dataset overview. So I'll take you through the simple project phases, and then we shall go through the data exploration, feature engineering, model architecture, performance, explainable AI, plus finally we shall go through the impact. Um, so, our data collect our phases were um, we had the first phase was data collection and preparation. Then we went to our exploratory data analysis, then feature engineering, model deployment, development. Sorry, then hybrid system integration, explainable AI, and finally deployment. So when we go in our data collection, the key points we had the data had 14 14,145 records with over 31 columns. We handled missing values and duplicates. We also um, did feature engineering, and so uh, so um, so there were 14,145 records with 31 columns and 121 duplicates. So, and in our exploratory data analysis, uh, exploratory data analysis, most orders were between 1 to 3 units. And the top products was the NPK 17, which comprised of 29.1%. And then tarpaulins, the top districts were Butale, Judge, and Jojo. And the seasons, mainly it was planting, which contributed 63.8%. And then testing, which was around 34.4%. Hamatic bugs contributed 91.7% with maize, 84.2, and then coffee. So this is our product distribution. The products which had the biggest impact, we have the Hamatic bugs, which had 91. Then the tarpaulins and with around 27, and the NPK 17, and we also have then the other products. So this we analyze distributions, categorical variables, and time series patterns during this phase. And the next phase, which was feature engineering, um, we created temporal features, diversity metrics, and interaction features. We added the year, month, day of the week, and days since first order to the current order. And then we also created input diversity metric and aggregated features were the district average quantity, season average quantity, and then the interaction features which were added, that was a season product and district product. So these features were mainly added for since the system was all about agricultural prediction, and some of these features were highly needed for these models. For instance, the reinforcement models required, which are mainly which are for inventory, required to understand when the orders were made, understand the average quantities and the season product, all that. So our data had part of the data was there, and some of these features were not there. So that's brought us to the feature engineering phase, whereby we had to add these features. Then the model development, several models were developed, which included the regression models, which where we had the linear regressions and XG boosts and very many other models, which we'll see during the other presentation in our next screen. And the key points during this model development was that several models were evaluated, and then key XG boosts showed great performance in regression models with an R squared that was around 0.99, which is 99%. Then a minimum average of around 0.000, so it will perform very well. And in the time series, the LSTM was best for the NPK products, since the time series models were trained on various products, not all products. And the profit was better for the hermetic bags. And in the reinforcement, deep chew outperformed the chew learning models, though it was trained on a very little time. And so in summary, the XG boost and gradient boosting had the highest, with a vaunting ensemble which combined the XG boost and other linear models to come up with a 99% R squared value. So this is our simple graph showing this. As you can see, the XG boost and linear regressions both kind of had high values, with the RIMA lagging out and LSTM having a 68, and our hybrid model, though this was done later, but we also came up with a hybrid model which had an R squared of 75%. Continuing to the hybrid system integration. Um, so our hybrid, like we had combined several models, which was the DQN, XCG boost, and other various models, plus the knowledge distillation, which we also did to come up with a hybrid model with a balanced feature importance. And we used sharp, sorry, uh, yes. Then in our hybrid system, we combine the XG boost LSTM and DQN plus the ensemble model, which was a combination of the various linear regression models to come up with a vaunting ensemble. And after adding up these models, we came up we included also a student model, which we had done distillation from the best performing linear regression models, and the reinforcement models. We came up with a student model, which we integrated with the existing linear models to come up with a hybrid model. And the hybrid scored a 75% R squared. With and during this process, the key points with the architecture was combined XG boost, LSTM, and DQN. Those were the major models. That's coming up with a final hybrid model with an R squared of 75 and RMSE of 3.03, which is not a bad performance after training and testing. And then the DQN limitations were negative, so we didn't train for a very long time due to limited resources and time. And then May and lastly, we had a balanced feature importance, and these are the summary hybrid R squared and its RMSE. Yes, this so in comparison, this is our XG boost with an R squared of nearly 1, then LSTM, and this is our ME. Then this is the profit plus our hybrid, which has an ME of 2.1 and an R squared of 0.75. Then we also did explainable AI, and during this process, we used the sharp thoughts come up to analyze all these models such that we are able in confidence of their predictions and understand some important features, why some models make some predictions, what do they depend on. So the key points, the DHN prioritized tools, And the XGBoost dominated by quantity and temporal features, which were feature engineered. And then the hybrid did a balanced feature importance from all the models. So that's why we had to combine such that we can come up with one conclusion or prediction which we would suit our current trend in Uganda. Then we use the sharp, those true value heat maps and other methods which were Lime, the PDPs to come up to our conclusions. And finally, it is deployment where we solve them as PK1, PTH files, and then we plan to optimize the DCN with prioritized experience replay, add external data, that is weather, trends, deploy as a microservice with monitoring. So saved around 5 models, and we have a three future improvements. This is the deployment timeline for model serialization, front-end dashboard, and deployment. It's measured in number of weeks. So thank you. Back to our official presentation. This was just one, shows the stages. So as we have gone, I've taken you through almost everything. So let us go for our data exploration. So these were the records and product usage. These are the figures, we've talked about them. And then the key insights, we have a seasonal patterns, fertilizer demand peaks were during planting. That's why we came to realize that planting season dominated almost the whole data set. And then the peak value was between March 21st, where we saw the highest activity of around 15,000 units plus. And then the regional hotspots are those are the districts which had the highest domination, where Butale, Jachinjuja, and Chotara districts, they show the highest activity. And then the data limitations, we had a missing land capacity data. So this gave us a very hard time to train these models for agriculture stock prediction, since these models require us to know like how much land is being used, so that we are able to predict how much quantity will be required or to input, and what could be the output after this. So this gave us a challenge, but we managed to go over through it. And we came up to the feature engineering insights, whereby we did the temporal features, month, day of week, and seasonal indicators. And then the diversity matrix, farmers typically used 7 to 8 different inputs from our data set. We realized the several inputs which were almost all farmers used to. Some used pangas, others used to go for the DAP and tarpaulins, things like that. And then regional aggregates are district-wise quantity averages, which were added in the feature engineering process. So this is our data overview with so this is these are the products, and then this is their quantity with the NPK around 40,000, then the tarpaulins 38 plus, and all of you then fungus contributed around 244 throughout the whole data set. Then the quantity distribution uh, raised up to 34, 34, 34, 46, 4,600 plus during over the time period which we used. That was between 2020 and 2021. And then the quantity over time from July 2020, this is how it kept on changing from the various farmers. This is how everything was changing. January 2021 with around 28, and then in March 12th. So this is February. Then and we come to August 2021. So it had a higher peak, and yes, this is how the data quantity was changing over time. Then the temporal trends, we had the various districts, and then the top quantity. Just as I say that these Butalija, Chenduju, Chotera, and the other districts showed the highest product quantity production during in this data set. As you can see, the Butalija scored around 7,600 plus quantity, with Chenduju around 48 plus. Yes, and then this is a feature correlation. As you can see, this is how the different features were correlate with the different different features, how they collaborate with each other. So this is was our heat map and as you can see, we have the various features, same features, but we want to know how does, let's say, corner correlate with the phone number. So you can see that if it is a negative 0.25, so you may find that very few farmers may be ordered for the corn and something like that. So this is also very important. You need to understand how different features interact with each other to know that feature dependency, whether it is a negative correlation or positive correlation, such that we may know that this feature is important for this. So in our feature engineering, so I also talked about that, and this is all what happened. The temporal features were year, month, day. As you can see, I already talked about this in our pipeline, and this was our data processing pipeline, whereby we go through data, missing value treatment, encoded features, diversity matrix, aggregated features, temporal features, and final feature set. Um, yeah, so the notable patterns: seasonal purchasing fertilizers were purchased during planting seasons, storage products during harvest seasons, and seasonal indicators highly predictive of product type. Then the quantity patterns, we have matic bags show high quantity. Quantity is often around 11 units, and this is how fertilizers and other products are affected. Then the geographical patterns, we had districts which show preferences for specific products, and some products are district specific. And we also discovered regional aggregates will reveal distinct farming practices. So you realize that not all districts or places follow the same farming patterns. Yeah, and the technical implementation, modular design, each processing step encapsulated in its own method, and then reproducibility, fixed and random state of 42 for consistent splits, and data leakage prevention. We we designed a scalar fit only on training data, and then flexibility, 100 different target variables via parameters. So that's why our models managed to train and yield confident results. And then this is our feature importance sharp analysis. With an XG boost, you realize the most important features are district average quantity, and then the same for for the various weeks, and our hybrid, how for the various models we have the day of the week, how the features affect the various models, blue being the DHON hybrid, and the green being the XG boost. So as you can see, this is how various, let's say, products affect. You realize the district average quantity affects the XG boost most, and the hybrid and the DHON. So I've already gone through our feature engineering pipeline, then the model architecture. So this is more of a list of what happened. We did comprehensive evaluation of the multiple modeling approaches to capture agricultural input deep demand patterns across Uganda, and then predict the stock prices. With regression models, we trained around 10 models with linear ridge, less so elastic, random gradient boosting, XG booster like GPM and SBR, and the best performers, the XG boost, as you can see from our statistics. Yes, and also did assembling, whereby bunting ensemble took it all, and then the reinforcement DHON performed better with limited training. You can imagine how sometimes these models can, you know. And the X Giboost architecture. So these are the various architectures of these systems, and they have the hyperparameters and the key features. Uh, mm, yeah. So the key features of the X Giboost gradient boosting framework, and tree pruning, regionalization to prevent overfitting, and parallel processing. And the LSTM, its optimizer is Adam, and then the learning rate was around 0.01 with a loss of MSE. And epochs, there were 100 epochs, and the batch size of 32. So this is its network structure. Then the hybrid system combines multiple models, as I said, to leverage the identification. And then this is how some of these models contributed to our to come up or to make the hybrid. And the top features are driving predictions in all this is quantity. So the extreme dominant of quantity suggests that potential data imbalance issues. Yeah, though we tried to do some feature engineering and exploratory data analysis, the data was still a bit imperfect. So this requires us to train these models more and more and continue improving them with time to make very, very confident and accuracy predictions. And then our performance, this is our table of how all the models performed, as I said, and then the knowledge distillation results from distilling complex models into smaller deployable versions. There was model reduction, event speed improvement, and performance drop. Yeah, like improvement. Uh, during knowledge distillation, our key improvement is that as we started from around negative 120 r squared, we managed to push up to negative 0.76. And by the time dip, we did our hybrid ensembling, we had come up to 0.75. So that's a very great improvement, as you can see from our hybrid system, based overall balance for real world deployment. Yeah, the performance by product type, as you can see, and then the limitations: missing land capacity, short time span, limited weather, and had some challenges. And then the feature work is incorporate weather and the market data and extend our D2N training, implement transformer architecture, then develop product specific models. So this is our sample visualization of our final, how they all performed with the final hybrid around 0.75 XG boost and student model enhanced student model, then linear regression, and our D2N, as I also said, it is negatives. So yeah, this is how everything. So this is our squared comparison. Then now we did some multimetric comparison for the RSM, R squared, and then MAE to come up with this graph, which is these are normalized values. You can see the hybrid, and then you can have a look at the final hybrid, and then yes, this is how it has been relating with all the other models. Yeah, at the ensemble, yeah, ensemble model, then student. Yeah, so that's how they have been. That's the comparison, and then when we go to the prediction comparison, comparing all the models in terms of prediction, we realize. So we come up with this, and first all the models says that we can see the difference of what we're talking about. Yeah, yeah. So um, so this is our actual quantity, minutes. So our actual quantity is in black. So this is how our actual values work. So during training and everything, we came up to realize to make a and see compare the actual predictions and what these models are actually predicting. So for the XG boost, this is how it varies from the actual. As you can see, it's in blue. So and then have the linear regression, how it was variating, then the student model, not very far. Each one, since it's in negatives, you can see that its our predictions are not very good. And then our final hybrid almost aligns with the actual predictions, as you can see. Um, so these are its predictions, and then when we compare it with the sorry with the yeah the actual ones, you realize they're almost the same. Yeah, then all for all the models, the actual predictions, realize our hybrid lies almost with the actual predictions. Then for the explainable I already explained that what we did, that we did model interpretability comparison, where we compared the various models, and then we came up to insights for each model, and realized the prepared actions and the Q value, whereby for the DHN we tested the increase, hold, and decrease, and selling, do nothing, all those were tested, and realized that it prioritized tangible inputs over like tools, storage of fertilizers, aligning with our Ugandan farming practices. And we also, for the XG Boost model insights, we also did that. As you can see, those were the results, plus finally the hybrid insights with XG Boost, Lithium, and the DHUN, how they contributed, and it used the DHUN output as counterbalances to XG Boost predictions, creating a more robust system. So those are the main insights. So the practical applications for farmers and policymakers plus distributors. For farmers, we use sharp plots, prioritize inputs based on season. And then for policymakers, allocate subsidies based on feature importance. And then for distributors, optimize inventory using Q level heat maps. And so these are the practical applications for this explainable AI, how it is applied. Then the value proposition, building why it's done. We build trust with our models, and then uncovering patterns, and then to guide improvements on how we can improve these models. For instance, we identified model weakness that led to concrete improvements, such as adding weather data to DHUN and the temporal features. And the AI techniques applied that were sharp analysis, quantified feature contributions to individual predictions, which revealed how each variable pushed predictions higher or lower. And then we had feature importance, ranked variables by their overall impact on model predictions, and then Q value heat maps and partial dependency dependency diagrams showed how predictions changed uh, when varying a single feature. So all these visualizations are in the paper, which will be shared too. And then the Q value heat maps, so we visualize how the DHN model valued different actions across inventory states, making aerial decisions interpretable. This is demonstrated here in my presentation. So this is the sharp summary plot for the various models, XGBoost hybrid and the DHUN, with a sharp value feature for the features and the over time. So this is how these features affected these various models. Uh, yeah, so this is a summary. Then this presentation will also be shared in detail, and it will also be accessed. Um, yeah, so this is the sharp dependence plot quantity of the feature and quantity. So for the hybrid model, feature value of around 1.38, then the sharp value is around 1.02. Yeah, so we are comparing the features and how everything was, they came up to affect the conclusion and predictions of these models. Then the explanation of a single prediction, you see how quantity contributes around 80% with maybe the district average quantity, and then how the product average quantity, everything, how they contribute to come up to this final prediction, and how they weight and add up. Then to demonstrate how the DHUN values, what we talked about here, whereby we said um, well, we visualized how the DHUN model valued different actions across inventory states, and yeah, these included here, where we say we tested the low stock increase, then medium hold, and then high stock decrease. So these are some of the states under the preferred action with our Q value. So when we come and we try to see, you realize that so if when does the model say do nothing, you do nothing, for instance, when demand is 0, inventory is 10. you have a lot of things, but the demand is zero and the quantity value is high. So what the models will do nothing. They're not going to restock or do anything. And same when the inventory is zero and again the demand is 10, so you again do nothing. So when to order maybe when inventory is 10, demand maybe zero, and then the Q value is around 5.69, and then when inventory is 8 and the Q value is around 8.42. So when you realize in the purpose when we follow our heat map, so the 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 decision to order is very little with these values, but once inventory is kind of equal to the demand and the Q value is almost equal, so you have to make one. So yeah, so these are the various demonstrations of this. Then lastly, we go to our impact for farmers, distributors, retailers, and policy makers. As we said in our first slide, the expected impact to reduce price volatility through better forecasting, optimized inventory levels, improved decisions, and policy support. So these support all these our system supports for farmers better decision making, as we have seen how our true models come up to tell you the action of what to do and how our various other models have been predicting. And then so these are for the policy makers and the distributors, how our system impacts them. And then the challenges, economic environment benefits, reduced operational costs, and fertilizer waste and runoff. So the project annual savings, farmers save up to 20%, with distributors 25% saving the environment. So the future expansion with the integration, market price data, regional expansion, mobile app deployment, satellite imagery, and then edge computing, that is implementing some IoT. And the key takeaways, the system predicts, optimize, empower, and then sustain accurate forecasting of agricultural input demand, and price enables proactive planning for stakeholders. So these are our key takeaways. So the agriculture stock prediction transforms raw data into actionable insights, bridging the gap between technical modeling and practical practical agriculture needs in Uganda. And so uh, it's the success hinges on addressing data limitations and scaling model deployment to maximize impact across agriculture value chain. So this is our impact metrics dashboard. As you can see, the waste reduction up to 18% with cost saving of 22% and 7% yield improvement. And then the current adoption rate, which is still very, very low. Then the district level analysis, as we saw from our data exploration, adoption rate and waste reduction, all that if our system is considered. Yeah. Then impact metrics over time, the waste reduction compared to the current waste, which is this from our data and current trends. And then so we realize once it's integrated to how to reduce. And then the price volatility, our prices are always changing and shifting over time compared to after the integration, and then the profit increase. Yeah. Then the impact summary, waste reduction up to 34.9% with price volatility and profit increase almost at the same time. This around 24.9 and 25.0. Yeah, so this was the agricultural stock prediction system. Thank you very much.